Hey everyone, Houston Math Prep here, following up on our vector fields introduction video. We want to introduce also to you line integrals, the idea of what a line integral is and how to calculate one, both using a scalar function and using a vector field. So if you remember in single variable calculus when we first did antiderivatives, we looked at the integral from a to b of some function of x dx, and this was an integral over the real line. You had an x-axis as a horizontal axis, and we integrated from some point A on that axis to some point B, and we were integrating this function which was a height, and that was over the real number line. And then we move into multivariable calculus, and we look at iterated or multiple integrals, where we're doing a double integral over a region, or we're doing a triple integral over a domain in three-dimensional space. And these integrals are over either the two-dimensional plane, or this integral here would be over some three-dimensional region. So a line integral is none of those things. A line integral is a way to integrate a scalar or a vector function, we'll go over both types, over some curve in two-dimensional or three-dimensional space. So not just over axis or not above a region, but actually over a curve in two or three-dimensional space. We can use it to find all sorts of things. Work required to put a satellite in orbit. We could find the mass of a wire curving through three-dimensional space. You could evaluate the surface area of a curtain under a curve. You could calculate voltage generated around a loop, find average temperature along a path. Lots of different things that we can do with line integrals that we can't necessarily do with other types of integrals. Looking at line integrals of scalar functions on a curve. So here I've got some curve, I'm calling it C for curve. P0 is going to be my starting point for the curve. P1 is going to be my ending point for this curve. Now this curve is in two-dimensional spaces in the xy plane, and we have some, looks like a paraboloid shaped function, some z equals or f of xy equals. Here's the function of that, and basically we're defining every point above the curve as it's moving in the xy plane to be the height of this function. And then one question we might ask, one of the things we just mentioned was, how do I find the area of this curtain? Well, we could do it similarly like we did with Riemann sums, at least to think about it. We wouldn't actually do that and calculate it that way. But if you think about breaking it up into many sections of curtain and maybe approximating with some sort of rectangle above a piece of the curve. So we'll go ahead and take the area of one section of the curtain. Now, if you remember with arc length, we called it S before. So here I'm going to call this a little bit of arc length as my width of my rectangle. So we'll call this delta S, some little bit of width. And then obviously the height here, when we multiply with that width, is going to give us one piece of the area, right? So we get our height times our width, which is delta S. Just like we do with all sums moving toward an integral, as I take more and more sections of the curtain and break them up into smaller and smaller pieces, as the number of pieces of curtain approaches infinity, then this delta S is going to get really small, and it will tend toward what we call ds, and we'll be adding up an infinite number of those things. And so our total area under the curve, this curtain here, the total curtain area, is going to be the integral of our function of xy integrated ds. And now we have this interesting new notation here where it's integral with a c below it, and that says, okay, we want to integrate over the curve C. That's our domain, not a region R, not a domain D in two or three-dimensional space, but a curve, which is actually, this is a one-dimensional object that is curving through two-dimensional space here. So what the heck does it mean to integrate over this curve? How do I do that? So what we'll actually need to do to sort of quantify our curve as some sort of a formula, think about it's a curve through space, we'll need to parameterize our curve C as some vector-valued function. Remember, we usually called that R of t when we did vector-valued functions before in multivariable calculus. In order to complete our line integral, that's what we'll do, is we'll parameterize our curve. We're going to look at how to calculate this starting at the idea of arc length. So if you remember arc length, if you did this application of vector-valued functions, the arc length of some curve through space, which we probably called S, was equal to the integral from a to b of the magnitude of r prime of t dt. So we had our vector-valued function in two or three-dimensional space. We took the derivative of that, we took the magnitude of that, and then we integrated that dt from the value a to b and got our arc length. So if this definition holds true, then that means if s of t is this integral here dt, then we actually know that ds is equal to this magnitude of r prime of t dt. And that's going to help us in our formula here, that we have this integral over my curve f of xy ds. So we need to go ahead and drop that information in there if ds is that thing. That means if I can define everything in terms of t, then I will integrate from t equals a to t equals b my function of x and y times the magnitude of r prime of t dt. So let's look at a first example. We want to evaluate the line integral of 2x squared plus y squared over some curve ds. Our curve is going to be a counterclockwise path over the circle of radius 2 centered at the origin. So you imagine here's a circle of radius 2. We're going to travel once around counterclockwise. And you want to think about on the function, which is 2x squared plus y squared, so it's an elliptical paraboloid, above my circle, if I project that upward, I get this sort of roller coaster looking path on that elliptical paraboloid. And the question is, what is the area below that function, right? This pink surface area region we're trying to find. So the first thing we want to do is set up our circle with radius 2 counterclockwise. We want to parameterize that as an r of t. So we'll go ahead in this example and say that r of t, if I want to travel clockwise around a circle of radius 2, you might have an idea that the parameterization of that circle is going to be 2 cosine of t, comma, 2 sine of t. And now I'll definitely need bounds, otherwise I'm going forever on the circle. I just want to go once around. So we'll also go ahead and say that t should be from 0 to 2 pi when we're taking one trip around the circle of radius 2 there. I have my parameterized curve. This is going to help me assign values in my function of x and y, and it's also going to help me get the magnitude of r prime of t. If I look here, my 2 cosine of t is what I'm going to put in for x in my formula, and my 2 sine of t is what I'm going to put in for y in my function of xy. Okay, so we know what's going to go in there. Let's go ahead and get our r prime of t so we can find the magnitude. So r prime of t is actually going to be, if we take the derivative of 2 cosine t, we'll get negative 2 sine of t. And then we'll get the derivative of 2 sine t is 2 cosine t. So we get something similar. That's our r prime. Now we will need a magnitude, right? So we'll go ahead and say the magnitude of r prime of t. And remember, that's the square root of each of these things squared and added together, right? So if I take the square root of this thing squared would be 4 sine squared t, plus if I take this thing squared, that would be 4 cosine squared of t. And if I have the square root of all that, well, think about if you factored out a 4, you'd have 4 times sine squared t plus cosine squared t. And sine squared t plus cosine squared t is just 1, right? So this would actually just be the square root of 4, once you use Pythagorean identity there. And so we get that the magnitude of r prime of t is actually just 2. Okay, so we have all of the things that we need to plug into our formula. So I'm going to go ahead and begin my integral. So I will have that my area is equal to the integral from a to b is going to be from 0 to 2 pi. Those are my t bounds. And now if I plug my x and y for my parameterized curve into my formula, then 2x squared is going to become 2 times 2 cosine of t squared, plus y squared would be the 2 sine of t all squared, so 2 sine of t all squared, and then times my magnitude of r prime of t, which was 2 from here, dt. Okay, so we'll do this integral. We've parameterized, we've plugged in our x and y values, we've found our magnitude of r prime and assigned our bounds, and now this is just something that you can probably do. Okay, I think I will at least pull out my 2 at this point out front. So we'll have 2 times the integral from 0 to 2 pi. Let's do a bit of manipulating in here. So if I square this, this would be 4 cosine squared t. I get a 2 out there, so that would actually be 8 cosine squared t, plus here I just have 2 sine t squared, no 2 in front, so this will be 4 sine squared t. So it's not just a number in here because we don't have the same coefficient for each term, but that's okay, we can still do this. I'm going to go ahead and bump out a 4 as well, so I'm going to divide everything by 4 and pull 4 out maybe in front. So let's say 2 times 4 in the front would be 8. We'll have the integral from 0 to 2 pi, And then we'll still have a 2 cosine squared t plus a sine squared t dt. Now, to integrate this, one of these cosine squared t's could be combined with the sine squared t to make one, but I would still have a cosine squared t left over, right? So I would have 8 integral from 0 to 2 pi, and I would end up with 1 from one of these and this, but I would still have a cosine squared t term left. And we're pretty close to being able to integrate this. Remember, with even powers of sine and cosine, a good thing to do is use double angle formula. So we would go ahead and say that this is 1 plus, if you remember, 1/2, 1 plus cosine of double the angle, right, which would be 2t. Okay, and we'll integrate that. Actually, let me go ahead and distribute the 1/2 and combine some like terms. So if I have 8 integral from 0 to 2 pi, think about I have 1, distributing the half, I would get another half, so that would actually give me 3/2 plus, and then I would have 1/2 of a cosine 2t as well. And now this is easily integrated at this point, so we'll keep the 8, and if we integrate 3/2 dt, then that becomes 3/2 t. And if I integrate 1/2 cosine 2t, antiderivative of cosine is sine, and the reciprocal of 2 will come out, so we actually get a plus 1/4 sine of 2t. And we'll evaluate from t equals 0 to t equals 2 pi, and that will give us our answer. Let's go ahead and do that. So we'll get 8 times, if I plug in 2 pi here, then I would get the 2 reducing with the 2 there, so that would give me 3 pi. Plus, if I take 2 pi and plug it in there, 2 times 2 pi would give me 4 pi. Sine of 4 pi is 0, so this whole term is 0. Minus, if I plug in 0 here, I would get 0. And plugging in 0 here, sine of 0 is also 0, so we get another 0 there. It looks like we get 8 times 3 pi. That's going to give us an answer of 24 pi for our line integral here. Let's look at another one of these that's just a little bit more complicated. We want to evaluate the line integral 2x ds along first the parabola y equals x squared. So this is y equals x squared here. And we're going from 0, 0 to 1, 1, so this is 1, 1 up here. And then what we're going to do is return to the origin along the line y equals x, so going from 1, 1 back to 0, 0. What we'll need to do is actually find the line integral along this first piece of the curve, and then we'll need to find the integral along the second piece of the curve. So this is actually 2 separate line integrals. To do this, let's go ahead and set this up. So I'm going to call this first one C1, my first curve, and I'm going to call this C2, my second curve. Okay, so we'll need to parameterize both of these curves. So let's go ahead and see. C1, I'm going to call my r of t. Now I need it so that y is equal to x squared, and I go from the origin to 1, 1. So I'm going to parameterize this way. I'm going to call this t, and then if I call xt, I'm going to call y t squared, right? Because y needs to be x squared. So if I called xt, then my y value must be that thing squared. So we call this t comma t squared. Now, can I figure out what my bounds need to be for t to start at 0, 0 and end at 1, 1? I think if you look at this, you might be able to figure it out, right? So to start at 0, 0, definitely we need to start at t equals 0. And to end at 1, 1, I actually need to end at t equals 1. So that's the parameterized version of my parabola, y equals x squared from 0, 0 to 1, 1. Let's go ahead and look at our second piece here. So I actually have our r of t being a different formula here, right? If you've done any parameterizing of a line in 2 or 3-dimensional space, you might remember that the way we can parameterize that is by plugging in the starting value and using the vector that gets you from the starting point to the ending point. So if I start at 1, 1, then each of my x and y components are going to have 1 as the constant in there. And the question is, what's the vector from 1, 1 to 0, 0? Well, it would be the vector that goes -1 horizontally and -1 vertically. And those negative ones, if you remember, they end up being the coefficients for your t term if you have a linear path. So 1 minus t is actually how we'll set this in here, and we'll go from 0 to 1 as well. Okay, think about when t is 0, then I'm starting at 1, 1 here, and when I hit a t value of 1, both of these are 0, and this is linear. Okay, so now remember what we're going to do. We're going to need to find r prime to do the integral, and we're also going to need to have things to substitute into our function here, 2x. So for my first line integral, my x is t and my y is t squared. In my second line integral, 1 minus t is the x, and 1 minus t is also the y. Okay, so let's go ahead and set up this first integral here. So actually, C1, we would have our bounds are 0 to 1. And if my function is 2x and x is t, then that makes that 2t. And remember that ds is the magnitude of r prime of t dt. So the magnitude of r prime, what is r prime for this first one? Well, if I take the derivative of t, I get 1. And if I take the derivative of t squared, I get 2t. And we'll multiply by the magnitude of that. So we'll start that in a minute. Let's go ahead and set up our second curve integral as well, right? So this straight line integral, so we'll have that will be from 0 to 1 because we also have 0 to 1 bounds here. Now 2x, in this case, for my second curve, x was 1 minus t, so that becomes 2 times 1 minus t. And then the magnitude of r prime of t dt, so the magnitude of the derivative of these. So the derivative of 1 minus t is going to be -1. And the derivative of 1 minus t again is going to be -1 again. So that will be the magnitude that we find and help us integrate there. Okay, let's go ahead and go back to our first curve now. If I want to, let's go ahead and find our magnitude. So this would equal the integral from 0 to 1 of 2t times the square root of this thing squared plus this thing squared. So 1 plus 4t squared, if I square both of those things and add them together, dt, right? And we'd integrate that. Okay, let's go ahead and do that. I think we can do that with a u substitution nicely. So if u is 1 plus 4t squared, then du is going to be 8t dt. And what I have is 2t dt. So if I divide this by 4, that would give me 2t dt, and that would be 1/4 du. So we will get here 1/4 integral from, now these are t bounds, I'm going to leave them as t bounds and come back to them. So t equals 0 to 1, and then I just get the square root of u du. Now that's u to the 1/2, so that'll be a power rule. So we'll get u to the 3/2, and then dividing by that 3/2 would be like multiplying by 2/3. Remember, these are 0 and 1 for t, not for u. If we go ahead and resub back, so here, let's see, 2 over 12, that'd be 1 over 6. We would get u to the 3/2 is going to be 1 plus 4t squared, all to the 3/2. And we will evaluate that from 0 to 1. And let's go ahead and plug in, so we'll have 1/6. If I plug in 1, I get 1 plus 4, which is 5 to the 3/2. Minus, if I plug in 0, I get 1 plus 0, which is 1, and 1 to the 3/2 is just going to be 1. So that's our first path. Okay, let's look at our second piece of the line integral here. So we will have the integral from 0 to 1. Let's do our magnitudes. We have 2 times 1 minus t. The magnitude of this, I would have the square root of this thing squared plus this thing squared. This squared would be 1, this squared would be 1. Add them together, we get 2. So the magnitude of that vector is root 2 d. dt. And now let's go ahead and bump some multiples out, right? I have a 2 here and a root 2. Let's move that out front just for good times here. Okay, so 2 root 2 integral from 0 to 1, 1 minus t dt. And then if we integrate, that's easy. We get 2 root 2 integral of 1 is t, and integral of t is 1/2 t squared. And now evaluating from 0 to 1, we'll plug in. So if I plug in 1, let's see, I get 1 minus 1/2. And if I plug in 0, I get 0 minus 0. And this is a half here, so I think the half will reduce with the 2 there, and we'll just get square root 2, right? So I have this much plus this much over here, so if we bring these together and make one answer out of it, let's go ahead and say 1/6. There's a nicer way to write this 5 to the 3/2. Think about this half means root 5, and 3 of those, I would have 3 copies of root 5, which would be 5 root 5 minus 1. And then we would also have plus square root 2 as well. Okay, lastly, let's do one example of a line integral in 3-dimensional space. You can tell because we're using the helix, and this helix has 3 components. We have an x component, y component, and z component for our vector. So we know we're in 3D space. Also, the z here in our scalar function probably gives that away as well. So we're going to integrate the function of x, y, and z here. It's actually just y and z, and we'll still use times the magnitude of r prime of t dt. So the first thing we'll need to do is parameterize our curve, except, oh look, it came to us already parameterized, so that's nice. But let's go ahead and label some things, right? So this is going to be what I put in for x, what I put in for y is here, and what I put in for z here. So you can see we only have y and z, so we'll just be using these 2 pieces in our function there. What I'll also need, though, remember, is I will need r prime of t. So let's go ahead and write that. So r prime of t is going to be, if I take the derivative of these, I'll get -3 sine of t. 3 sine of t becomes 3 cosine of t, and then the derivative of t is just 1. I already have my t-bounds. Those were provided to me, so that's nice as well. Let's go ahead and figure out the magnitude of r prime. So the magnitude of r prime of t, well, that's just going to be the square root of all these things squared added up, right? So square root of, if I square the first thing, I'll get 9 sine squared t. If I square the second one, I'll get 9 cosine squared t. And if I square 1, I still get 1. So we get 9 sine squared t plus 9 cosine squared t plus 1. And now this term and this term, if you add them together, actually give you 9. So 9 plus 1 is going to give us that our magnitude of r prime of t is root 10, and so that's what will go in there. Let's go ahead and set up our integral now. So we'll have the integral from, my t-bounds are 0 to 2 pi, so integral 0 to 2 pi. My function is a y minus z, so I'm going to go ahead and put in there y minus z, so that's 3 sine t minus t. 3 sine t minus t times r prime of t, which is square root of 10 dt. And now this is not so bad to do, I think, right? We could go ahead and bump the root 10 to the front if you like, so we could say square root 10. Let's go ahead and evaluate this integral, though, right? The antiderivative of 3 sine t, that's going to be -3 cosine of t. The antiderivative of t there, so we'll have a minus, and then we'll have a 1/2 t squared. And we're evaluating from 0 to 2 pi. Okay, so if we plug in, so we'll keep our root 10 out front for sure. If we plug in 2 pi, -3 times cosine of 2 pi. Cosine of 2 pi is the same as cosine of 0, which is 1. So this is -3 minus, if I plug in 2 pi here, so I'm squaring the 2 and the pi, so I get 4 from squaring the 2, but I also get a pi squared, right? So let's remember the pi squared, but now 4, half of 4 is going to be 2, right? So I actually get 2 pi squared. there. It's a little bit odd, but it's okay. And then if I plug in 0 here, I will get -3 cosine of 0. Cosine of 0 is 1, so we get -3 there. Minus 1/2 times 0 squared would be 0. You can see what happens with the 3's, right? We have a -3, but then we get a +3 there. So we just get our root 10 times the only thing left in there, right? So it looks like we'll get, let's write it, -2 root 10 pi squared, perhaps. Okay, hopefully this has given you a good introduction to line integrals and how they work with scalar functions. Our next part of this video series is talking about line integrals using vector fields. So we're actually doing a line integral over a vector field instead of a line integral over a scalar function. Those are a bit different, so you can check those out. Thanks for watching, everybody. We'll see you in the next video.